60 Oxford versus 60 Garden. I know that Professor Eric Cornell was confused and was probably thinking about his EDM talk and so on. But I was right on because Professor Michel Lukin has shown me this place a few times in the past, and I knew where I'm going. And it's actually have to admire the quantum initiative at Harvard. This is incredible. I visited here last year and oil and looking and said, well, this is the place we're going to have a new building. And came earlier this year, the building was already here. And now we have the first ITAMP conference. So it's a really great pleasure. And thank Pete for setting up all the documented discussion and the motivation. I actually took the slides out so I can just jump right into the technical details of some of the clock. And I'm going to start with my discussion as a quantum engineer. I know these days it's a fashionable word, but I'm not trying to be fashionable here. It's a scaling up a quantum system as my motivation to kind of connect different quantum systems that we are working on these days in the laboratory. Pete made a very nice presentation about atomic clocks already, and I'm just going to give you a very quick rundown of, currently the measurement precision of atomic clock has achieved at the level of 10⁻20, and you can such that you can measure gravitational redshift over just a small distance of few hundred microns. The accuracy Pete mentioned has reached the 10⁻18 digits now. And even quantum entanglement is starting to play a role. For example, you can use cavity QED to entangle a bunch of atoms, or use neutral atom tweezer arrays that you can use Rydberg blockades to entangle 5, 6, 10 atoms together and actually demonstrate real quantum advantage. All of that is telling you some of the interesting directions of what the clock is moving towards. So it's actually interesting to think back a bit of where did all the atomic physics physics started. I think in the 50s and 60s, we all heard about, I was not born, but we know the pioneering work of mass power spectroscopy. You have nuclei embedded in the solids, and he told us the gamma ray, despite the huge recoil momentum, can actually be absorbed by entire crystal. Therefore, you can actually see fairly narrow transition. At the time, of course, mass power spectroscopy is completely incoherent. But this was a big lesson. I think the pioneers in trapped ion community really learned about this lesson, and they understand it was the Lorentz force. You can put a single particle, charged particle in the middle of ion trap, and with laser cooling and so on, you can really reach the so-called Lamb-Dickey regime where you can remove all the Doppler shift. And we neutral atom folks really took that lesson from trapped ion people and saying, okay, instead of working with one atom, can we work with many, many atoms, but still enjoy the stopper-free transition without recoil? And it would be poetic. It's actually coming back to mass power spectroscopy and turning incoherent excitation. And I think that's probably, to me, the most exciting aspect of the nuclear clock. You can guess where I'm getting to. When you get to the nuclear clock, it's the fact that you can maybe have Avogadro constant number of quantum observer in your clock is the most exciting aspect. Nothing else. For that, you can really start to dream about doing tabletop fundamental physics type of discovery, because I can have 1 gram of salt without cooling, right in your vacuum chamber. And put a photon in there and actually see the weight of the salt went up by e to the mc squared. These are the things where I think it can be tremendously exciting, and we get to hear Igor Pekovsky talk about this specifically in that area. So I want to make that connection there today. For me, when I started my independent career around the year 2000, was really tremendously lucky. The Violence group, Pete Schmidt at the time was actually, you were postdoc in 2006, 2004 or 2003. But you came to Boulder, and remember I entertained you with dinner and so on. So at the time, we really worked out this quantum logic clock, and this one was a particular picture from Jim Berquist in the middle, where he trapped the single mercury ion at the time was the best atomic clock. And on the other hand, in the neutral atoms undergoing revolution. Here's a picture of Eric and his colleagues, where most Bose-Einstein condensate was just made in the middle of the 90s. And Debbie Jin quickly followed, it made a degenerate Fermi gas. So as a young faculty member, you can think of, okay, what if we put all these atoms in an optical lattice? There's one more trick you have to play, which is just like a trapped ion, where the Lorentz force that's trapping the particle is independent of the clock state. Well, if you can come up with some ideas like Hattori and Jeff Kimball, when I was a postdoc with him at Caltech, come up with an idea where you can confine the atoms such that the external degrees of freedom, where the trapping potential is going to control, and the internal degrees of freedom, which is the spin or the two orbits of the states that you use to build a clock, is independent of the trapping potential. Then you can separate the two degrees of freedom. And that sort of, it gives you the recipe of, here's a picture which we can potentially have hundreds of thousands of atoms confined in a lattice, potentially achieve quantum coherence of a few hundred seconds, but potentially with strontium has a very long-lived excited state lifetime. And this picture has largely come to a reality. Now we can have 2 minutes of coherence time with something on the order of 100,000 atoms in that. So with this, we started on following that recipe, and here's a picture where, yeah, that's nice. You can see that we started not with a 3D trapping, but rather just a one-dimensional optical lattice confines into the two-dimensional trapping potential. You put a dozen of these atoms in there, and these are identical fermions. It turns out, of course, when the measurement precision goes further, you can start to see these fermions also interact through the P-wave interactions. And the only requirement for fermions is that wave function has to be anti-symmetrized with respect to exchange of two particles. And so the anti-symmetrization can come from the motional degrees of freedom. This minus sign gives rise to this anti-symmetrization, and that's the so-called the lowest order partial wave, the P-wave interaction. And we can see all this P-wave interaction gives rise to frequency shift. So there's some limitation of how many particles we can jam into the system like this. There's a frequency shift. Well, moving forward a couple of years, the idea now of this kind of a frequency shift can be dealt with by making the potential extremely shallow, where the so-called Varnier-Stock lattice clock, it was developed about a couple of years ago. The potential is, instead of confining these atoms in hundreds of recoil or tens of recoil trap, we now turn this down to about 10 recoil trapping potential. And it's because of it's under gravity, the lattice is oriented under gravity. You can see between neighboring sites of the trapping, there's a NGH kind of energy lift, which is a gravitational energy, potential energy difference between these neighboring sites. And so the lattice looks like a Varnier-Stock lattice in the condensed matter system where the electrical field is used to bias the system. So in this case, the wave function, because of the trapping potential is so shallow, the wave function, in fact, is actually well spread out. And if you think about, we are using this so-called matched wavelength trapping, the ground state and excited state, electronic states share the same trapping potential. And so the wave function is spread out, and that allows you to drive the transition, but on the same site to achieve a very long coherence time. Here I'm showing as just 3-second Rabi line shape. But you can also drive off sites because the wave function has a non-vanishing component. So you can drive from site I to site I plus J, for example. These are experimental data showing you can drive so-called Varnier-Stock sidebands, and the line shape is extremely narrow, indicating very, very long coherence time. And you can measure actually gravity, because the difference between the Varnier-Stock sideband and the carrier is exactly NGH, the gravitational potential energy. And so we can also use this technique to build, just getting used to Pete's fancy tool here. You can use this to build also, kind of an interesting interferometer where you prepare coherence for position between the ground and the excited electronic state. And you just keep driving the ground electronic excited state into different parts of the Varnier-Stock lattice, such that in the end, you have a coherence for position between spin up in lattice site in the upstairs with spin down in the basement. And so this is actually, it's an interferometer that allows you to measure time and the gravity at the same time. This, in fact, is a picture of how our first attempt of using this as atom interferometer to measure gravity. At the same time, we can measure the time. So this this type of work has been going on also in Holger Miller's group, in Murray Holland's, and so on, that's inside the lattice to do atom interferometry. But this one achieves very long coherence time, just like in the clock. And I want to come back to the scaling. Because the trapping potential is so shallow, the wave function is spreading over several different sites. Now you can have on-site interaction, which is a P wave, as described earlier, those are identical fermions. But between neighboring sites, because the wavelength of exciting the clock transition is non-commensurate with lattice sites, such separation, you can have non-identical fermions, but their wave function overlap on top of each other, so you can have S-wave interaction. If you control the lattice trapping potential, such as shown here, while measuring the fractional frequency shift in the clock, you can see the frequency shift is a function of the trapping potential, essentially dialing in your Hamiltonian, how much you want to control the S-wave, P-wave contributions relatively to each other. And you can get into the point where at a certain trapping depth, if you zoom in, you can actually see that at this particular trapping depth, the clock shift is actually vanishing at the level of 10 to the -20. And you will have no density shift at this point. What about coherence? It's also interesting that you can look at the so-called D gamma. This is the decoherence rate, or Dn. N is the number of atoms per pancake. And you can see this decoherence rate comes down, also goes to the minimum somewhere at this trapping depth of the 10 recoil. And it's actually great to see, this kind of a decoherence rate. Here I'm showing a picture of 93 seconds, but we have seen decoherence rate, lifetime coherence time not approaching the lifetime and beyond. In fact, the beyond is just because the atom which decayed away by spontaneous emission removed itself from the trapping, and you can actually see coherence time longer than a lifetime. And nevertheless, as I'm implying to, there's still D gamma Dn. There's a still dependence of N-dependent decoherence rate. In order to get to this very long coherence time, you still have to dilute. So that means there's still limitation in this kind of a 1D trap. And perhaps what we really need to go to is go to 3D. But nevertheless, you can take advantage of this kind of trapping long coherence time to make advance on clock precision, and using the longer coherence time. For example, this year, we are now demonstrating clocks at 1 second, you can reach precision of 1 × 10⁻18. So really it only takes 10 to the 4 seconds to reach 10⁻20 in terms of the measurement precision, how well you can measure things like gravitational redshift and so on. So if you want to continue to go on to scale up the number, another game you can play is entanglement. Suppose the number of atoms is really limiting our coherence. How do we effectively increase atom number? Is keep the same number of particles in the system, but it allow them to entangle with each other. And that would certainly play a game where you can continue to improve on the measurement precision without incurring the systematics or decoherence effects that we're talking about. Of course, entanglement has its own bad things that you have to control, and the decoherence and so on brought up by quantum measurements. These are the extra degrees of freedom that you have to be careful with. In this particular rendition, in our experiment, we actually built this 1D lattice that looks like an elevator that you can go in and out of a pair of highly reflective mirrors, the cavity QED, sort of a Jeff Kimball rendition of the cavity QED system. And you can entangle sample A and then move them out, entangle sample B, and you compare them. And indeed, at this level, taking the pioneering work from Valadin and so on, using the cavity QED to do the entanglement generation of a bunch of atoms in there, you can start to compare two clocks with both spin squeezed and show advantage of a couple dBs at this very feeble advantage at the moment. But nevertheless, it's a spin squeezing at the 10⁻17, not quite at 10⁻20, really push the envelope kind of a level as a genuine quantum advantage. But it's interesting to continue to push along this direction to see how much can we push advance the state of the art using quantum entanglement in clocks like this. This is another way of increasing the quantum system size. And as I mentioned earlier, well, maybe one natural way to increase scaling up the system is build a 3-dimensional crystal. This, in this case, is an artificial crystal made by 3 pairs of interfering laser beams. And suppose I have a degenerate Fermi gas samples of millions of atoms and put them 1,000,000 of those atoms together in this crystal with coherence time of 120 seconds. That's a clock that's not bad. You know, at 1 second, you will see a precision of a few parts to the 10⁻20. You average 400 seconds. Shimon Kokowitz dreamed about in 2016. He said that we can use this to detect gravitational waves. And so this was one of the key motivation for us to develop the 3-dimensional crystal with a Fermi gas. But of course, as soon as you pack these many atoms in there, the atom-atom interaction becomes a big deal. And could this be a limitation for measurement precision or accuracy? Or is this, depending on whether you're a pessimistic person or an optimistic person, this turns into the best quantum playground to do quantum simulations and quantum sensing? And in fact, this is actually true. You know, if you look into this kind of a Fermi-Hubbard model, we have a tremendously complicated competition mechanism of tunneling versus on-site interaction versus how you drive the quantum system with a Rabi drive with a phase difference as a laser beam propagating through the crystal. There's all kinds of interesting physics come out of this. And then you can just forget about you're a clock person. It just becomes, you know, quantum simulator. But it's interesting, you know, you can connect quantum metrology, quantum simulation in a very nice way. It's very genuine. You know, to understand spin orbital coupling, how the super exchange interactions, something that Misha Lukin and so on proposed this mechanism to do quantum computing, took effort of Emmanuel Bloch and so on to see those effects. But these days, it just shows up as a 1 second oscillation in our very long Ramsey frame to coherence time. You can study collective dipolar coupling band shifts because each atom has enabling atoms. And you have to really think about this in a non-trivial way, how each atom is, in fact, it's a vacuum system being modified by its surrounding particles. It's actually quite interesting cavity QED system. You can even think about this as a ultimately testing of you know, van der Waals interaction where each individual particles are sitting with a certain distance from each other. And you can experience van der Waals interaction, you can directly measure with a clock shift. And it relates to Kashmir force. If you can turn this into an accordion lattice, you can expand the distance between these particles. You can actually verify the 1/R7 sort of a distance dependence between the radiating dipoles. So these are the interesting areas that we are quite much taking our hat off as a clock maker, but putting hat on as studying complex quantum system, but all in the sort of a game of trying to scale up the quantum system, eventually pushing for the measurement capability to reach the discovery potential of fundamental physics. But however, if you have powerful friends, right, instead of making all these crystals by yourself, well, what if you call up Vienna and ask somebody else to make the crystal? So now I'm going to bypass this slide, just because it's really complex. We were looking into all the coherence time. We can do a 3D crystal. We can turn into a 2D pancake. We can turn it into 1D Cuban cigar. We can make a 3D crystal. And you can see all kinds of interesting coherence time as a function of the dimensionality and interaction. So it's a rich playground. But suppose you say, now I want to become a clock again, and I still want to make a big crystal. Well, then the best is to call heroes like Thorsten and so on. You know, he can make a crystal where there's a nuclear stuff, a nuclear transition nucleus like thorium that's embedded in calcium fluoride crystal. The reason why this is so exciting is to think about his doping concentration here. He's using the number 4 × 10⁸ per cc. Well, I work a little bit with quantum gas, degenerate quantum gas. The best numbers we get is 10⁻14 per cc. And in order to get it 1 centimeter cube, that requires huge optical power. And Thorsten maybe is just cutting his teeth right now. Maybe he will tell us eventually he will get to 4 × 10⁻22, 10⁻23. Challenge to you. Thorsten is going to give a talk about next how to make crystals. But we were really interested in this kind of number to scale things up. And indeed, he shipped us a crystal in May, and we put this in a VOD comb, and you can see this crystal as a fluorescent a little bit. And this is where we are turning into a nuclear clock exploration. So again, I want to reflect back on mass power spectroscopy when everything started on this kind of recoil-free transition move. In the early days, of course, it was looking at the nuclear decay, and the gamma ray gets out, and it can be absorbed by another nucleus nearby. And in this nucleus is embedded in a crystal. You can actually do recoil-free sort of absorption of the gamma ray. And it's a poetic connection also from that regard, just walking a couple hundred meters away from here, there's the alignment laboratory. And I was told, actually, I gave a lecture recently in Harvard Colloquium. Afterwards, John Doyle's friend, colleague approached me saying, not only the first redshift measurement, the famous pound replica experiment of using gamma ray to measure the redshift of the photon, it was done in this building. This building was named after Lyman. In fact, he is the one who did all the VUV spectroscopy also. So there's a lot of a historical connection to this place here in Cambridge. But we were making some cheesy connection between atomic and nuclear connection. We'd say, oh, Harvard people did this back in the 60s to measure the redshift that required them to have several flows of lights to measure the photon energy shift difference. And here we use a few hundred microns, and the atomic clock is so good now, can measure redshift right within the atomic ensemble. But real connection really comes when you actually have a real nuclear clock in coherently driving it. And that, I think, lies real tremendous opportunity to do fundamental physics here. So the thorium transition has been around for a while. I think it started with a pair of Russian scientists in the 70s observing a little energy difference between two gamma ray photons. And they pinned down that, oh, there must be another excited state in the nucleus that's about 3 eV above it. People went and searched for this transition for a long, long time. Nobody found it. And the field got damped down a little until about 10 years ago. People say it's not 3 eV, by the way, it's 7. And that rekindled people's interest. And you can see over the past few years, the nuclear physicists, especially people at Munich, University of Munich, really pinned down Tirov, Professor Tirov, really pinned this energy level down to something around 2 nanometers. 2 nanometers for nuclear physics, that's incredible precision. For atomic physicists or for optical physicists, this is it. What are you talking about? That's kind of a level of uncertainty where can we build our laser around? And so the experiment really opened our eyes was actually the experiment done at CERN last summer. They not only made a better precision, but what was a key revelation was they can embed the thorium atoms in the calcium fluoride crystal. This was a crystal also made by Thorsten. And they saw direct observation, they made a direct observation of decay, fluorescence photon decay by the nuclear decay. And that really opened our eye. We thought, well, that's a crystal we would like to get hands on to. So earlier this year, there was a pair of papers coming out from PTB in collaboration with Technical University of Vienna with Thorsten's group, where they used four-way mixing and nanosecond Q-switch lasers. They were able to generate 10 gigahertz line with lasers and drive these transitions directly and observe fluorescence. This work was soon followed by the group of Eric Hudson at UCLA. Did the same thing with a different crystal. So we thought if you really want to narrow this transition down, notice this structure is so broad. There's understructure of a nuclear transition that's not being resolved. So in order to really go to high resolution, maintaining high resolution and maintaining with a good enough excitation, we figured you got to keep the spectral brightness at the same way, and that yet get this transition much, get this line width of the laser that radiating the nuclei to be much narrower. And fortunately, we actually been thinking about this problem for a long, long time. And there are people who have pioneered the field of attosecond physics told us, if you have a pulse that's strong enough, you can distort the Coulomb potential and it generates so-called high harmonics. These are high harmonics of the fundamental laser that's driving this process of attosecond process. And some people call it harmonic cone, but don't be fooled with that. It's not. This is not a cone. It's a harmonic spectrum. That's true. But You can call it comb, but it's not a comb in the sense of a frequency comb where you can actually maintaining phase coherence one after another. And in order to really make the comb, the one way to think about doing it is repeat this process over and over. Instead of having one isolated nanosecond generation pulse, you repeat the process every 10 nanoseconds, or you repeat the pulse fast enough where the phase coherence is walking away. That's the whole point of the lesson from Jian Hao and Ted Hinch was, if you want to generate a true frequency comb where you have a high spectroscopy resolution, you have to make sure you control the optical phase. And the only way to control optical phase is by having repeated pulses. Let's say you can control the phase from one to the next. And so that's the lesson. The technical challenge is, well, if each pulse needs to be, on the order of 10 to the 13, 10 to the 14 watts per centimeter square, and you want to generate a pulse one after another after 10 nanosecond delay, that means the power, the average power you needed to put into the system is tremendous. And there's no amplifier, active amplifier can do that. This was the idea that back in 2002, Jason Jones and I started to think about putting the frequency comb into the build-up cavity, matching each frequency comb with each cavity mode, such that you can in some sense, build the entire pulse inside the empty cavity to have a circulating power that approaching kilowatts. And this was actually in 2005, the first success of starting to generate from converting IR frequency comb into the XUV frequency comb. And our very own Dylan Yost, sitting in the audience, he's going to give a talk soon, that he was a graduate student at the time and really helped push demonstrating the very first so-called VAV comb spectroscopy. So we started generating frequency combs into this spectral region. So at the time, we don't have a nuclear transition. We're just cutting our teeth on atomic transitions, argons and neons. But nevertheless, the concept is really simple. Once you have these frequency combs, how do we demonstrate the comb really has the power of resolving narrow transitions? And we decided to make a beam of atoms, neon or argon, and just scan the frequency comb across these narrow transitions and see whether we can have somewhat Doppler-free spectroscopy using very, very collimated atomic beam. And indeed, this process was successful. We were able to show, transition that can be resolved at 10 megahertz or so on these very high line atomic states in argon or neon. Neon, we actually went down to 63 nanometer. And notice the fourth transition I'm going to tell you about, thorium, is actually somewhere 150 nanometer. So it's not even as challenging as neon. And if we can push this technology further to this place here, I know this is going to be challenging, but there lies the next nuclear transition, which is the uranium. It would be fantastic if we can do the uranium clock instead of atomic bombs, do peaceful use of nuclear technology. So anyway, that's a little bit of a distraction here, but the same idea, as soon as we have Thorsten's crystal in the lab, you can immediately see that's why we can so quickly get the nuclear transition resolved. Well, we already have this frequency comb, just scan over this nuclear transition. And indeed, as you do this, you combine speed and precision all in one, because there's all these lines. The only shortcoming of this is that each individual line of the comb has a limited power. We wish this power is much, much bigger so that you can drive fast Rabi rates. But that's the system. This is the Thorsten's crystal. This is the parabolic mirror to reflect all the fluorescence onto the photodetector, photomultiplier. And on the first night, Chang Kun, I should have comment on the 3 students who made a huge contribution to this work sitting in the audience. I will later show you a picture. So the first night, they will start to see that, the transition start to show up. And then following 1 week times 24 times 7, literally speaking, because they didn't sleep. They scan all this line out. And you say, well, it's just 5 lines. How come it took them that long time? And it turns out they had to record to make sure these are real nuclear transitions, not some feeble atomic transitions. They have to check on the fluorescence over the time scale of several hundreds of seconds. And it's really true. These nuclear states live for a very long time. If you zoom in, you can scan across this nuclear resonance. And if you look at the lifetime, This resonance, by the way, that's what we are heavily working on currently to try to narrow down this line by improving on the frequency cone. But if you look at the fluorescence decay, it really literally takes 10 minutes for each event. And that's why you have to keep, this is our bottleneck right now. The so-called quantum state detection is our bottleneck. We are trying to find a way to get help. Just like Pete is asking for help. I'm asking for help to find us a way to drive the nuclear transition and use nuclear quadrupole spectroscopy, nuclear magnetic spectroscopy, or connection to another atomic state to allow us to read out the quantum state really quickly, because I don't want to do fluorescence measurement on every point. That's just a bottleneck. But I'm confident this will work out in the coming days, coming months. So this now allow you to connect. Shimon was very kind of picking this as a symbol for the ITAMP conference. That's what actually he came to invite me, saying we are about to hold a fundamental conference, conference on fundamental physics. Are you interested in coming? And I was hesitating a little bit. Shimon said, "Please come." And I said, "We just have a result on nuclear transition. Can I talk about this?" He said, "Why not?" and so he said, I sent him this picture, and he said, "Well, this is so beautiful. I'm going to make this as the symbol for the conference." and so here it just connects. It almost comes naturally when you have these two frequency cones connected in frequency. The ratio comes out with 13 digits, of course, limited at the moment by the thorium transition by the line itself. But what's exciting, maybe tell you a little bit of the follow-up work. Since we first observed this nuclear transition is, the first thing you see is there's 5 lines. There's actually more lines. And for the moment, we're focusing on these 5 lines because we can identify them exactly arising from the nuclear quadrupole splittings of the ground state, which has a nuclear spin of 5½ The isomeric state, the excited state is 3½ And you can see these 5 transitions exactly match, and you can apply some rules and so on. In fact, that's the way we found the weakest line, which is 10 times weaker. From that, you can immediately plug into this Hamiltonian that govern the interaction of nuclear quadrupole moment with the electric field gradient inside the crystal. So you have this, cylindrically symmetric, incompressible liquid model of the nuclear volume, and this it's got to carry the quadrupole moment. And you subject this to electric field gradient with so-called anisotropic factor eta, describing the difference of the gradients between x direction and y direction, with the quantization axis defined in the z direction. Then you plug this into the spectroscopy figure, you can immediately measure the product of quadrupole moment times the electric field gradient, and as well as determine the asymmetry point of the electric field gradient between x and y direction. And these are the numbers that we fitted from the experimental data points. And if you take the ratio between the excited state and ground state, and of course the VZZ drops out, and you have the excited state ground state ratio. From that, you can then convert, because we know that directly we know the nuclear moments, the spin of each nuclear state. We can convert this from the laboratory frame ratio of the quadrupole moments into the body fixed frame. That's the body fixed to the nucleus itself, and that's the ratio. From this ratio, you can actually calculate, you can do modeling this, thanks to Mariana Safronova, and she went ahead to do the calculation and show that the volume between the atmospheric state and ground state is actually different at a 4th digit, instead of the previous assumption that the volume is always the same. So now you can start to see the precision spectroscopy like this, similar to Pete. You do precision spectroscopy, you start to actually confining nuclear physics in a way that nuclear physicists had not been traditionally doing those kind of precision measurements. And this has consequences, because they're talking about sensitivity to new physics that Pete spent a lot of time on. If you look at the sensitivity, suppose the alpha fine structure constant does change, which alpha governs all the electromagnetic field interactions. And in nuclear structure, of course, you have a balance act between strong force and the Coulomb interactions. So if you look at, because now you have a more precise knowledge of volumes changing between the ground state and excited state, you can actually do a more precise calculation to determine how much Coulomb interaction energy actually changes when you go from ground state to excited state. And it turns out this is the change in about 50 keV. But of course, we are measuring is the frequency difference of the transition of 8.4 eV. So automatically, this gives you the sensitivity enhancement factor, because really the underlying physics that's driving, if alpha is changing, how much energy is this going to change, is underlying pedestal is a 50 keV, even though we are sitting on a very small transition of 8.4 eV. So this is going to be quite interesting in the future, in order to really make better confinement, better constraints on these nuclear models, and as Pete also alluded to really to make claims on discovery of fundamental physics and so on, will require us to do better measurements on nuclear physics, including maybe even higher order moments, like octopole moments and so on. And we don't have a clear ideas how to do that, but we would love to learn new ideas here. And I think there's a satellite conference that's going to be held here on Saturday, right after this. You can also use this to study material science. For example, the crystal structure, instead of focusing on the quadrupole moment, you can imagine you put this crystal on a vibrating table and just let the crystal vibrate. But that will control the stress. That would influence the electrical quadrupole moment. In this particular measurement, we just simply heated up the crystal, cool the crystal by varying the temperature, and you can already see electric field changes, electric field gradient changes, electron charge density changes, and that can move these resolved nuclear quadrupole splitting structure in a way that allow us to fit this Hamiltonian, determining all these sort of, in some sense, material structure using nuclear transition to probe. And so indeed, as we change the temperature from room temperature to 150 Kelvin, you can see different transitions move differently. And there's a particular transition, for example, has accidental cancellation between the electron charge density change and the nuclear quadrupole moment change. And you can get to the point where, oh, it's hardly ever dependent on the temperature. And so you can plot these nuclear quadrupole moment times the product of the electrical field gradient as a function of temperature, or you can plot this asymmetrical parameter eta as a function of the temperature. But together with the sum rule, you can actually calculate the quadrupole shift. You can actually sum them in certain ways where the center of frequency, the synthesized center of frequency, does not depend on the quadrupole shift. And that frequency can still move. This is the so-called absolute shift. This red line still moves. That's because the electron charge density around nucleus is changing, and you can determine that quantity as well. The point I want to make, you can, for clock makers, for metrologists, they will look at this line saying, well, it's not really straight. There must be temperature dependence, and that's true. And from this line alone, if you just have a crystal like ours from Thorsten, and you will say, if I want to get to 10⁻18 stability, what would be the temperature stability would be required? Turns out to be 5 microkelvin, just using this slope. But what's really interesting is that the fact that you have splittings, you can actually drive, suppose NMR or NQR worked, you can actually build the co-magnetometers or co-electrical measurements to actually measure the in situ, the crystal parameter. At the same time, you pick the best transition in between the ground state and excited state. So you have a minimum sensitivity to the external parameter, but external parameter itself can be measured independently. And so it feels almost like we're really confident to drive the precision to 10⁻18 is going to be straightforward. Whether you can claim accuracy all the way down there, that remains to be seen. So that's another really interesting aspect of how do we build these different co-thermometer, co-magnetometer, co-electrometer, and so on, to help us to characterize the crystal and continue to guarantee the precision and accuracy of the nuclear transition. I want to end my talk by one more exciting development that's in collaboration with the UCLA, Eric Hudson's group. So this is a Thorsten's crystal, how he grew this crystal, and he's going to get into the details of this. And I can say this really, really beautiful system, about centimeters in size, a few millimeters, and it works. You know, we can see narrow transitions. And I think at the moment I showed you a 200 kilohertz line width, and I blame ourselves first. Our laser probably is not good enough, so we're going to keep working on that until we start to see few kilohertz line width and start to see inhomogeneous spotting. It'll be really, really interesting time, because we will study line width, how the center moves around, We change the magnetic field, electric field, temperature, and all of these things can be worked out and bring under control. Once we can measure it, it can be controlled. So it's going to be very exciting. Nevertheless, it requires large amount of material. I think one of the key delay of our result was because we were trying to send our nuclear material from Boulder to Vienna, and it was not possible. It took us long time. And also once the crystal is made, it's still radioactive. I don't think Thorsten can put this on a plane in his pocket and go through the custom, and he will be arrested probably at the entrance.
You won't need to tell anybody.
Yeah, we won't stay here. Yeah, okay. The Zoom is not being broadcasted. Hussein guaranteed us that. And then so, we were interested in building our own at the time. We actually been working on this since 2018 to build a thin film. And the reason why we like thin film is because in principle, this uses much smaller amount of material. And if you can see narrow line, which we haven't seen yet, but if you can do that, this in principle is a much smaller amount of nuclear radiation. And this one you can certainly carry around. It's just because as long as they allow you to carry bananas on board, you will be able to carry this on board. It's the same amount of radiation. So fortunately, we have also powerful friends on the West Coast, led by Eric Hedison's group at UCLA. They have those lasers. Our frequency cone, we were trying to scan the thin film. At the time, we were also trying to use photoelectron detection. We haven't seen narrow lines yet. There could be several different reasons. One is the doping level is maybe not quite, the density is maybe not quite high enough. There could be broadening mechanism that's going on. We just need to do further investigation on this. But Eric has this forward mixing laser, the nanosecond 10 gigahertz line with laser. And we sent this to UCLA. And they put it under their laser, and they can see this very broad transition, just like in the crystal. And so this is again 10 gigahertz wide. And what's really interesting from this observation is depending on what material we use as a substrate on which we develop the thin film, the line width is different. We don't know exactly the reason why, but you can speculate. Maybe there's some collective. After all, you actually got about 10 to the 7 emitters in the volume of the wavelength. It's a strongly coupled system. Of course it's inhomogeneously broadened, but this may be, suffice to say, maybe this is a starting point of the nuclear quantum optics. Start to look at it, collective decays and so on, kind of interesting dipolar coupling that I mentioned briefly in strontium crystal. So it's a very exciting starting point on this. So I want to end here. Hopefully you heard the message of scaling the quantum system up, and nuclear physics brings us a new capability of scaling things up inside a kind of a potentially room temperature device. And that's really the most interesting aspect of that work. And I want to recognize, of course, many graduate students and postdocs and collaborators for the strontium clock, and for nuclear physics, we have the three, Tian, Changkun, and Jack. They're all here in the audience, and thank you very much for your attention.
Thanks a lot, Jun. I didn't want to interrupt the amazing finish to that talk. So we maybe have time for 1 or 2 questions, and then we can ask more questions over coffee.
Thanks for the great overview. What is the limiting factor concerning the line width of your home?
Okay, yes. We actually did it. In fact, a few years ago, we used the one fundamental laser to divide it into 2 copies of XUV cone. And so 2 independent cavities, and we'll bring them back to interfere. We can actually see line width as narrow as a hertz. So meaning this attosecond physics is actually amazingly coherent. Now I have 2 separate sort of attosecond generations. I bring them together to generate 2 separate XUV cones, and we bring them together in sort of 1 hertz speed. What's limiting us right now could be, well, that measurement only measures the common mode, right? In some sense, the common mode is the laser that's driving them. And the differential part, which is attosecond physics, is confirmed to be very coherent. But my laser itself, if that has a jitter on it, it's common mode. And so what we believe is our fundamental laser itself, we just use the 1064 field kilohertz language laser. We did not use silicon crystal to drive the transition and so on. So I think it's limited by the fundamental frequency combs phase noise, which gets amplified up to the 7th harmonic. And that's the part we're working on right now.
One more question? Yeah, there.
Yeah, so.
Oh, I don't know if this is one doing the same kind of phone thing. I guess it's loud now.
And so I was wondering about this small interval super long fluorescence.
Yes.
Is it possible there's an added cavity to provide constant?
Yes, if we can do cavity QED with nuclear transition, that'll be great. No, this is exactly the point of the cavity, like bring quantum optics into nuclear physics, if we can do that. At the moment, of course, we're talking about have mirrors, what kind of high finesse at 148 nanometer, how that's going to deal with the crystal, and there's a lot of uncertainty. But in thin film, if that works, that's exactly the goal. I didn't show a slide, but in principle, if a thin film works, that's a thin film thorium fluoride grown right onto a mirror. So it's that's cavity QED right on there. The thin film itself is part of the cavity. So this will be great, that I use cavity QED to do the readout. But I also think we know how to do, when I say we know, the community knows how to do nuclear magnetic resonance, nuclear particle resonance, and so on. I think we'll try to figure things out where you drive from one nuclear state to another nuclear state, you just simply read the magnetic moments with enough sensitivity. That would be the state readout. Hopefully that can be a millisecond state readout instead of 20 minutes of fluorescence decay.
All right, let's thank Jun and Pete again. About 20 minutes for coffee. We'll start again at 10:50.
Pete, thank you so much.
Yeah, you're welcome.